A vector is a quantity that has both magnitude and direction. Magnitude is the length. For a vector in a plane, it's convenient to use an arrow to represent the vector. The length of the arrow represents the magnitude, while the arrowhead indicates the direction. Vectors can be represented on a coordinate plane as arrows drawn from an initial point, called the tail, to a terminal point, called the head or the tip. Symbolically, vectors can be represented as a bold lowercase letter, such as a V, or much like a ray, for example, RP. However, the arrow on a vector does not mean it continues forever. It simply indicates the direction of the vector, which terminates at the indicated point. So when I'm looking at this guy, we're starting here at R, and we're going towards P. This is the length or the magnitude of the vector, and this arrow represents the direction that it's headed. Here's some vector vocabulary. So we'll start with components. The A component is the horizontal component, and the B is the vertical. This is the ordered pair used to represent the vector. If vector V has point x1, y1, and terminal point x2, y2, then you can find the components by subtracting the second x minus the first x, the second y minus the first y. The length or the magnitude uses these absolute value bars. If V is equal to components A, B, then the length or the magnitude, we use Pythagorean Theorem. So this would be A squared plus B squared. And let me show you what that looks like on this vector above. If you have some horizontal component and a vertical component, this is just a right triangle. So if we wanted to find the length of this vector, we would just take the horizontal component, square it, and the vertical component, square it, and take the square root. And that's what Pythagorean Theorem is. The direction, and we're going to use theta, is a rotation angle from the positive horizontal axis. If vector V, AB, and A is greater than 0, then you find theta using the inverse tangent of B divided by A. That's when A is greater than 0. So I'm going to say it's a positive A. Okay, if you have A that is less than 0, so in this case we'll have a negative A, you're going to use inverse tangent again, B divided by A, but this time you're going to add 180. And then the last case would be if A were to equal 0. If you have no horizontal direction, then your vector is going to either go straight up or straight down. So we'll say that theta is either positive or negative 90 degrees. And let me put a degree symbol on those. Okay, so now we've got some basic vocabulary. Let's take a look at a few examples. We'll just work one of each of those cases. So I'll just start with this vector here. Okay, and I believe this vector is labeled T on your worksheet. And so if we're working with vector T, the horizontal component will start from the tail and run along the x-axis 4 units. Okay, so let me draw that. Those 4 units. And then it's going to be running vertically to the tip 3 units. So I can write my components for vector T as 4, 3. Hopefully you recognize that this is one of our Pythagorean triples, a 3, 4, 5 triangle. So the length of that vector is 5 units. In order to find the angle, the rotation angle, this is my little theta guy right here, we're going to use inverse tangent. So I'm going to set up my equation, tangent inverse, the b value, remember this is just alpha order, AB, so it's going to be the b value divided by the a value. My a is positive, so all I have to do is inverse tangent of b divided by a. Okay, so let's take a look at that because I don't know what inverse tangent of 3/4 is. You can go to Desmos. I don't have a graphing calculator at home either, so we're going to be using this. You know that you can just evaluate inverse tangent without having to worry, like you don't have to graph on this. So I'm going to work through it. There's inverse tangent. And what was that? 3 divided by 4? Okay, so that's in radians. I know I'm not going to have an angle that's 0.64. So if I use my settings, I can change that to degrees. So I have about 36 point, if I round it to 1 decimal, 36.9 degrees. And that looks, if I'm looking at this rotation angle here, we definitely know it's acute. It's not quite bisecting, so we know that it would be less than 45. And so it's about 36.9. Okay, let's take a look at vector, let's see, we want an A that's negative. So how about vector V? This guy over here is vector V. So we're going to start from the tail. This time I'm going to the left 2 units because you're always looking at the horizontal component first, and then we're going to go down 1, 2, 3, 4, 5 units. Okay, so this one I'm going to have to do some math. I know I'm going to the left 2, and I'm going to go down 5. Okay, and here's my right angle. If I want to find the magnitude, I'm going to use those 2 values with Pythagorean Theorem to find the length of that guy. So for vector V, my horizontal component is -2, my vertical component is -5. This is my A and my B. This time, I don't know what my magnitude is. I'm going to have to work it. So it's going to be -2 squared plus -5 squared. I'm going to go back to my Desmos, and we're going to see what that is equal to. Okay, so let's see. I want the square root of -2 squared plus -5 squared. And so I can see that my length of that vector, the magnitude, is about 5.4 units. The last thing I need to do is find the direction. Since my A value is negative, I'm going to have to add 180. So inverse tangent, the B value divided by the A value plus 180. Okay, so let's see. I'm going to type in the word tangent, raise it to the -1. Open my parentheses. And then I don't know why that negative moved there, so I'm going to fix that. That's what I want. So that rotation angle is about 248 248.2 degrees. 248.2. And then let's just take a look at that. If the tail was at the origin, let me grab a color here so I can, and I rotate it around all the way to this vector, we can see that it's going to be somewhere between 180 and 270 degrees. And it makes sense for it to be about 248 degrees. Okay, let's try one more. Let's take a look at vector S. Vector S is going straight down. So we know that the horizontal component is going to be 0. Remember, if it's straight down or straight up, my A value is 0. My angle is going to be either a positive or negative 90. Well, hopefully you recognize that if you're going straight down, you're going negative 90 degrees. If you're going straight up, it would be your positive 90. So for vector S, this will be kind of easy. The horizontal is 0. The vertical is 1, 2, 3, 4, 5, but it's going down. So I know that my vertical component's negative, and the length of the vector is 5 units. The direction, since you're going straight down, is just negative 90. You don't need to do any math on that guy. A vector is said to be in standard position if its initial point's at the origin. When located in standard position, the components match up with the coordinates of the vector's terminal point. Define each of the following in terms of x, y, and magnitude. Okay, so since we are building right triangles with the horizontal and vertical components, we can use SOHCAHTOA. Okay, so for this guy, here's my theta. This is my x distance, my y distance, and this is the magnitude of the vector, the length of the vector. And the vector components for this guy, the horizontal and the vertical, x, y. So if I wanted to find cosine of this angle, well, cosine, let me write out my SOHCAHTOA. Cosine is the adjacent divided by the hypotenuse. So if this is my theta here, the adjacent's x, my hypotenuse is the magnitude. So this is going to be x divided by the magnitude. Sine is going to be the opposite over the hypotenuse. So sine of this theta here is going to be the y value over the magnitude. So y over the magnitude. The directions say to solve these equations for x and y to create formulas that allow you to find the components when the magnitude and the direction are known. So if I were to take this equation here for cosine theta and solve for x, x is being divided by the magnitude, I'm going to end up with, well, if we're dividing by something, to undo that, we use multiplication. So I'm going to multiply both sides by the magnitude of the vector. And so I'm going to multiply both sides by the magnitude of the vector. That is going to cancel it on the right side. And it's going to give me an equation, x is equal to magnitude times cosine of theta. So I'm going to write over here, magnitude of the vector times cosine of the angle. It works very similar for sine. Sine is being divided by the magnitude, so to undo that, let's multiply. That cancels the magnitude on the right, and we're left with y is equal to the magnitude times sine of the angle. Use the formulas derived above to resolve each vector into the component forms. And I'm not sure why, but my values did not show up. So let me see. The magnitude of this vector f is 12, and the rotation angle is 60 degrees. All right, so let's see. It's going to be magnitude. So the x component is going to be 12 times cosine of 60, and the y is going to be 12 times sine of 60. I'll need to go back to Desmos and calculate those numbers. Okay, here is my cosine, whoops, and there's my y component. So my x component is 6, my y component is about 10.4. So what it's saying is that this vector from the tail to the tip moves 6 units horizontally and about 10.4 units vertically. Let's try this again. Let's do this next one. So I'm given that vector g, this is vector g, has a magnitude of 8 units and a rotation angle of 210. So it's going to be magnitude times cosine of the angle for the horizontal component, magnitude times sine of the angle for the vertical. And I run back to Desmos and let's plug those in. Okay, so what we can see is that the horizontal component is about negative 6.9 and the vertical component is negative 4. And let's just make sure that makes sense. From the tail to the tip, we're moving about 7 units to the left and about 4 units down. And so that makes sense. All right, we're going to move on. Each item below describes a vector quantity. For each vector, provide a sketch, then tell the magnitude, direction, and components. Okay, so in the first problem here, we have a plane heads northwest for 50 miles. So first thing I'm going to do is draw a picture. So let's see. Let me just get my little north, south, west, east. So if I'm going northwest, I'm going exactly between those two. And I'm moving for 50 miles. So what I'm finding out is that the magnitude of this vector is 50 miles. So let's see. Well, what direction is this going to be? Well, let's see. What rotation angle divides this quadrant exactly in half? What is exactly halfway between 90 degrees and 180 degrees? Well, I believe that's 135. So now I have my magnitude and my direction. Let's go ahead and fill in some of these blanks down here. That's easy enough. Last thing we have to do is find our components. So now it's just going to be magnitude times cosine of the angle and magnitude times sine of the angle. So this is going to be your x component and this is your y component. And we'll have to visit Desmos again. 50 cosine 135 and 50 sine 135. So I'm just going to come back up here. I like to just kind of keep there's the horizontal and there's the vertical. So negative 35.4 and 35.4. Question B, a ramp has a 30-degree inclination. Okay, so this might be a little different. We have a 30-degree incline. So that means the ramp has a 30-degree incline. Now, a kid on a skateboard rides down the ramp 14 feet. So I'm going in this direction, starting here. Well, that makes this my tail. So I'm going to have to redraw this. Okay, let's see. I'll get rid of that. All right. Probably should have read the problem first. Starting here at the tail, 30-degree incline. That is this here. And I'm going in this direction. And the skateboard ramp is 14 feet. So I know my magnitude is 14 feet. This is my rotation angle. So we know that that rotation angle is not 30 degrees. From the tail to the tip, this rotation angle is greater than 180. Okay, so let's see. We know my magnitude is 14. Well, this horizontal line is parallel to this horizontal line. This would be considered a transversal. So we know from geometry that alternate interior angles are congruent. Therefore, this angle right here is also 30 degrees. The rotation angle is 180 plus 30. 180 would be the horizontal line, and then we're going to go 30 degrees more, so that means my rotation angle is 210. 180 plus 30. All right, let's find our components. Magnitude times cosine of the rotation angle, and magnitude times sine of the rotation angle. 14 cosine 210 and 14 sine 210. So let's come back over here. 14 cosine 210 and 14 sine 210. Okay, so it looks like we're going left 12 and down about -7. So negative 12.1, negative 7. All right, last problem. An airplane leaves the runway going 220 miles per hour. There is your magnitude. Flying at an angle of elevation of 15 degrees. Okay, there is your rotation angle. An angle of elevation, remember, is always from the horizontal. So this is my 15-degree rotation angle. The magnitude of this vector is 220. Let's go to our Desmos. The x component, magnitude times cosine of the angle. The y, magnitude times sine of the angle. Okay, so this airplane is going about 212.5 to the right, that's your horizontal component, and about 50, let's round that, 59, 6.9. So 212.5, 56.9. Okay, and we're done with our first lesson.